Hi everyone, welcome to another video for Kines 7103 where we're talking about dealing with outliers and influential error terms in our regression models. So in the previous two videos we've talked about leverage when we have variables that have significant variation in the x-axis, and outliers where we have residuals that present significant variation in the y-axis. So in the video today we'll be talking about how we combine those two measures into an overall measure of influence to talk about how an individual data point or an individual error term might be creating a substantial effect on our model that really changes the interpretation of our model, either in terms of the magnitude of the parameters or the statistical significance of the parameters, or both. So when we're talking about influential data points, we're really talking about combining unusual values in X, or the levers, and unusual values in Y, or the outliers that we've discussed so far. Combining these two factors, we can actually get different types of measurements of influence for the individual data points. So influence refers to the effect that a data point has on our model when it is present versus when it is absent. So you can think about if we fit our linear regression model with this data point included versus if we fit this the linear model with this data point excluded, how would those two results differ? And the idea is that influential data points can change our parameter estimates, both in terms of their magnitude, their statistical significance, or both. So we might have a situation where the inclusion of a data point makes the slope massively more positive than it otherwise would be. We could have a situation where the inclusion of a data point might make the slope statistically significant versus not statistically significant. Or we could have a situation like we discussed in the previous videos where the actual inclusion of a data point caused the slope to completely switch. And we went from a statistically significant positive slope to a statistically significant negative slope, all based on the undue influence that a single data point was having on our model. So these influential data points we often want to exclude and then refit our statistical models because we want our model to reflect all of the data and not be swayed by a single strange data point that is influencing the overall model. So the most common method for measuring influence in regression is something referred to as Cook's distance, which is denoted here by the letter D. So we have a D sub I indexing this for each data point, because for each observation that we have in our model, we can calculate a distance value for it. And as you can see in the equation here, Cook's distance combines outliers on Y, right? So we have our squared residuals in the numerator of this fraction, normalized to the number of parameters in model A multiplied by the standard deviation of the residuals, or the mean squared error in the denominator. And then we're multiplying that quantity by our leverage, right, which tells us about how much of a deviant this value is on X. So this is combining variability in Y, or extremeness in Y, with extremeness in X. And the variables that will have the largest effect are going to have large leverage and be large outliers. And if you deviate a lot in both of those directions, you're going to have a lot of influence on the model and ultimately be shaping the final parameter estimates and the statistical significance of those parameter estimates that we get. So Cook's distance combines this outlier distance with the leverage to get a combined measure of influence. We can see this across the plots that R gives us, right? So when we pass a linear model to the plot function, it gives us a series of outputs. And you have to click down in the console window, right, and press enter to see each plot in succession. But two of those plots I'm going to present here. So the first plot is actually just our original data. So this was the example from the chapter where we had a transposition error that led to one outlying data point when we were looking at SAT verbal scores against high school ranks. And we ended up with this statistically significant negative relationship when this outlying data point was included. One of the plots, right, that we looked at in the previous module was this standardized residuals versus fitted values, or what's known as the scale versus location plot, which shows us how much of a deviant something is as a residual against what the predicted value of it was. And here was that one outlying data point up in the upper right-hand corner. And we said this was an extreme Y value. And it certainly looked like if we took this data point out, we would end up with a very different regression slope than what we got when we included that data point. So if we keep clicking enter, right, in R, once we have that plot function set up, we will get a series of graphs, the last of which is this residuals versus leverage plot. So as we just talked about on the previous slide, when we're combining the residuals with the leverage, we're ultimately going to be computing Cook's distance. So on this plot, we have residuals on the y-axis, and these are the standardized residuals being plotted against the leverage on the x-axis. And so each of these reflects the residual and the leverage from our model. And then the dashed lines that R is drawing here show us Cook's distance values, which are regarded as sort of somewhat critical Cook's distance values. And in general, a Cook's distance value greater than 1 means that you have a data point that has a lot of influence and a lot of sway on your model. And as we showed, if we take out this data point number 6, that has a massive change on both the magnitude, the direction, and the statistical significance of our slope. So it makes sense that we have this very large Cook's distance value here for this data point, because removing that data point substantially changes the model that we're going to get out the other side. And we can actually see that if we look at the two statistical outputs for when that data point is included over here on the left versus when that influential data point is removed over here on the right. So we've highlighted that data point in blue now, both in the original graph and over in the residuals versus leverage plot. And what you can see is that we have the coefficients in the original graph. We have an intercept of 96.89 and a slope of negative 0.5 that is statistically significant. But that's mostly driven by this very influential data point, and when it has been taken out, this changes both our intercept and our slope pretty dramatically. So with that data point removed, we go down to an intercept of 8.3 and a slope of positive 0.48. So the direction and the magnitude of the slope entirely flip. The intercept goes down by about 90 points. We get a very, very different looking model when this one data point is removed. So that suggests that those parameter outputs or those parameter estimates that we were getting weren't actually very good. Our model was essentially being bent to fit a single data point, and therefore it wasn't a good representation of all of our data. So this is why we want to check for any of these Cook's distance effects to see if we have influential data points. That might suggest a data point that is there in error, right? There might have been some sort of coding or recording error in the data. Or even if those data are accurate, it might suggest an individual or an observation that doesn't really belong in our sample, and that might be an alternative reason for excluding it. So a large Cook's distance in itself is not evidence that we need to remove a data point, but it should force us to ask some questions about the values that we've observed for that data point. And then we want to compare our models both with and without that outlying data point to see exactly what kind of influence it has on the parameter estimates that we're getting. And in an ideal world, the exclusion of that data point won't really change our model all that much, and then our model would be robust to these outlying or influential values.